Okay, so in this tutorial, I'm going to look at this linked list example in C++. So this is basically, it uses a linked list with nodes, and it adds some functionality like push and etc. If you've recently learned about classes and inheritance and things like that, and also pointers, and this is a good review video where we're going to look at how to use these ideas to actually make some working code. You can look at my GitHub in the description if you want to get the code, although it will be a little bit more advanced in that repository. It'll just use templates so that you can use different types for your linked list and stuff like that, as well as a bit more functionality down here. But yeah, let's just get started and we'll look at this overview. We have this class node, and this just stores the double for value and the next node. And when we create an instance of this, we'll put in the value argument, and then we'll set this value to the value we inputted, and we'll set this next to null pointer. Now normally you would have like getters and setters for the value, and you'd have the actual data here in the private. So that's one change you can make, and that's actually something I did in the code that you'll see in the GitHub repository in the description. Let me see here. So yeah, it's private for the value and the next node, and then you have this get val, set val, get next, set next. But this also works, but generally you would try to avoid this. It's just easier for this basic example. So here we have this key value pair. I'm not going to talk about this. This is for the unordered map, like lower in the script. And this is our class linked list. So I wrote basically a vector because it has a lot of the functionality as the standard vector in C++. So I'll just go line by line and explain this. So we have this static int total linked lists. This just stores the total amount of linked lists that we've made, so you can keep track of this. And it automatically increments and decrements in the constructors and the destructor. So we don't have any private variables. We have a protected next node and a tail node. The tail node is useful for pushing to the back of the vector or of the linked list, since we can directly access the tail and then set the tail next to the new node. We'll look at this in a sec. And now we've got the public member functions. So this is the default constructor, where it sets the next and the tail to null pointer. It increments the total linked lists. And we've got this constructor that initializes the list with an initializer list. So here you can basically input your own list of doubles in this case. So yeah, just to make this clear, this linked list uses doubles, but in the GitHub repository that I've made with some more refined code, it uses a template so that you can use different types like integers, strings, whatever. So here we initialize it with the initial list. We set the next node to null pointer, the tail node to null pointer, and then for each value in the initial list, we'll push this value onto the linked list. We'll look at the push function in a bit, but this just adds it to the back. So you continuously add it to the back until you've added all of the elements. We also increment total linked lists by 1. Now this is the destructor because it's got this symbol. So we first decrement total linked lists, then the current node, we'll set this, this is just like a temporary node pointer, and we'll set this to next, which is basically the first node in the linked list. And then while the current node is not null, we'll use this temp, which we'll set to current. The current will be set to current.next, and then we'll delete temp. So basically this holds like the first node while current goes to the next node, and then you delete the previous node. You delete temp. So the only reason we have this temporary node is to hold the last node so that we don't lose like where we are in the linked list, or like we don't lose the pointer to the one that we're currently pointing to. Because if we just deleted current, then we wouldn't be able to access current.next or anything. So yeah. And then we make sure to set next and tail to null pointers so that we don't have any like dangling pointers pointing to memory that we don't have access to. Now we've got the length function. So this is quite an obvious edge case. If this dot next is null pointer, then we'll return 0 because there's no nodes in the list. And then we set this integer result to 1. We set this temp to this dot next, and then we just check while temp dot next is not null, and we set it to the next node, and we increment res, and then we return res. So this just basically continues hopping to the next node until we hop to the null pointer. So that's what this checks. And then here we have a bool empty. So this returns if this dot length is equal to 0. There's a lot of ways you can do this. You can also simply check if this dot next is equal to null pointer. There's many ways to do this, but we just reuse this code. Now we get to the void push. So here we input a double value of what value we want to push to the end of the linked list, and then we check if this dot next is equal to null pointer. Also, you can check if this dot empty, that's the exact same as this. So if it's basically empty, then we'll set this dot next equal to new node with this value. So you add one node, like the whole list is basically going to contain this one node, but otherwise you make this temp and you iterate through the list going this dot next until you get to null pointer. And then you set the next node to this new node with the value that we inputted. Like I said earlier, this can be sped up by using the tail parameter that we've kept up here. But in this exact case, we haven't used it. We've done it through just looping through the whole list. This takes O of n time complexity, whereas using the tail pointer takes O of 1 time complexity. So here in this case, you can see we use the tail pointer to set the next node. So this is a lot quicker, obviously. So yeah, let me see if there's. Yeah, here in the void push, we have we use the tail and set the next node to the node with this value. So yeah, you can see this implementation as well here. The T is just the type. So in our case, it was just a double. So that's the slight difference there. Now we'll look at this double val index. So it takes in an unsigned integer n, and this is just the index, and we have it unsigned because we don't want someone inputting negative numbers. And then we just check, we create this temp, set it to this dot next, so this is the first node. And then for like 0 to n, we basically just increment it and go to the next node in the list over and over again n times, basically. And then we've reached the node that we want to get to, so we'll return that node's value. The reason we have these two statements here is because if we hit a node that's null pointer, then we've gone out of range. There's a slight typo here, but we've gone out of range if it gets to a node that's called null pointer. So we just have these checks here, so it's more clear. Now we have this node pointer that returns the node at index. So this gets you the value at index, but this gets you the actual node at the index. So you can edit the value. That's the main reason this is useful. So yeah, it's basically the same thing. We just have this temp, set it to the first node, and then loop n times going to the next node. And then once we reach that node, we return temp. I did write a small comment here that this should be protected eventually, and we'll overload this operator to change specific values. So I believe that's what's done here as well. I won't go through this right now. But yeah, we'll see that. And now we have this double pop. So this basically pops the back of the of the list, and then returns the double of the value that was actually there. So we check if the list is empty, then we'll throw like an underflow error, so the list is empty and you can't pop back. If this dot next is equal to null pointer, that means one element is left basically. So we get this double return value, and then we'll set this dot next. We'll set the return value to this dot next dot val, and then we'll delete this dot next, and then we'll set this dot next to be null pointer just to reduce the risk of editing memory that we don't have access to, and then we'll return this value. Now otherwise we'll just do we'll just loop until we hit null pointer. So when we hit null pointer, that means we've reached the end of the list. So once temp.next.next is null pointer, that means temp.next is the last valid entry in the list, if that makes sense. So you get the return value by looking at temp.next.val, and then we delete temp.next, and then set the temp.next to null pointer so that it doesn't point to memory we don't have access to. We also set the tail equal to temp, and then we return the return value. So hopefully that makes sense. Next, we'll look at the pop front. So this, instead of going to the back of the list and popping, it just pops the first item in the list. So again, we check if it's empty, then we can't pop anything. Then we just check if there's one element left, and if there is, then we just basically get the value of the element, pop that element, and just update the next and tail to be null pointers, and then we return the value, similar to what we did above. And then here, yeah, I believe here we should also set this dot tail to be empty as well. That might be a slight mistake, but yeah, and then down here we basically set the we make this dot next point to basically this dot next. So we basically skip the first node with that pointer, and we also keep track of the return value, the value of the node we're about to delete, and we delete that node, and we also return this value. Now we have this function double front. So this gets the first element of the list. So again, we check if it's empty, and we throw an error if it is. Otherwise, we'll just return the first value. And here we check the back for double back. So this gets the last element, the value of the last element. And again, we check if it's empty, and we'll throw an error if it is. Otherwise, we just check the tail's value. So this is one instance of using the tail to actually make it more efficient instead of having to loop n times through the array. Now here we declared some more functions. So like swap values, and you input the indices of the left and right. We also have this quicksort, this sort, print, and find, and we actually define them externally outside of the class. So we'll see that in a sec down here using linked list : but there's two more here that we'll look at right before that. So sorry. Yeah, so we have this pop at index. So you input an index. So let's say you input 4, it'll pop the element at index 4. So first it checks if you want to pop the first element, and if you do, then it'll just pop front and return. Then if you want to pop a different element, it'll get this temp node, and it'll get access to node at index n-1. So it'll get access to the node right before the node you want to pop. And then again, it checks if this is a null pointer, that means it's out of range, so we'll throw that error. Otherwise, we'll just get this pointer to the node that we want to delete, which is the next node to temp. And then we'll set temp.next equal to temp.next.next. So it'll basically, instead of pointing to the node we want to delete, it'll point to the node after that and just skip it basically. And then we delete the node that we want to delete. So hopefully that's clear. Now we'll look at the pop find. So we input this double X. it finds the index of this value. So let's say you input 5, it looks for the number with the value 5 and gets its index. That's what this does. And we have this find, which we've defined above. This returns the index, and we'll look at this definition in a second. If the index is -1, we return -1. Basically, this doesn't exist, so we can't pop it. Otherwise, we will pop at index, and we already made this pop at index right here, which we just looked at. So this really shows how you can reuse code in different functions, and it's good for making your code much more concise and readable. So we just pop at this index, and then we return the index that we popped. All right, so now let's look at how we define the member functions externally out of the class. So we state the return type as usual, but then before typing the name, we have to type in the class name : : So in this case, linked_list : : and so in this specific swap values, we input the left and right integers or indexes, and we have this double temp that gets the value at index left, and then here we get node at index L, and we access its value and set it to the value at index R, and then set the node at index R value to temp. So this just swaps the two values, and we do it by accessing their values using the node at index, which we made above. And now we'll look at the quicksort function. So if you haven't learned quicksort, it basically chooses a pivot, and it puts all the numbers smaller than the pivot to the left and all the numbers larger than the pivot to the right. So this is, I believe this is the default sort function in C++ as well, when you have like a vector and you just write sort vector.begin and vector.end. So this is like, it's a pretty efficient way of sorting. I believe quicksort time complexity is O of n log n. So yeah, best case and average case is n log n. So it's pretty good sort function. So it's just the first one I implemented here. And I might implement other sorts later, but you don't really need them. Like you could use insertion sort, merge sort, etc., selection sort, but they're not as useful as this. And this is also a pretty simple implementation. So let's look at how it works. So if the start is greater than or equal to end, that means either we're pointing to one value or the start is after the end, which makes no sense. So we just return since it must already be sorted. Then we have this int pivot. So the way we choose the pivot is we just take the first value in the subarray. So we just set it to the start element in this case. There are other ways you can choose a pivot, but this is just the simplest way, and it works most of the time. Well, it works all the time, but it could possibly not be the fastest, but it's a fine way of choosing a pivot. Then we have this left, which is s+1, and right is e. So we basically exclude the pivot. And then we just check while left is less than right. And then here we just move the left, we just push the left towards the right until we hit a number that is less than pivot. So we basically hit a number that we should swap or move to the right of pivot. And then on the right, we do the same. We move the right pointer to the left until we hit a number that we should swap. And by that, I mean moving it to the left of pivot. And so once we found these two values that we need to swap, we just swap them. So we use our swap values, which we used before, and we swap the left and right. And then after completing this a bunch of times, all the left values are smaller than the pivot and all the right values are larger than the pivot. We swap S and R. So we move the pivot to the actual center of the subarray, and then we quicksort the left side and we quicksort the right side. So we exclude the pivot because the pivot's put into the right position. And now, hopefully this makes sense. We have this sort member function. So it just calls quicksort on the whole array from 0 to length -1. All right, and now we have this void linked list print. In the new code here, I have it set as virtual in case you want to override it. If you make, like, let's say you make an unordered map using this linked list or something like that. Or not an unordered map, but like a set or something like that, and you want to inherit all the properties from linked list, then you might want to override the print method. So you might want to call this virtual void linked list print. But here we basically just loop through all of them until we hit null pointer and we print the value, and then increment by going to the next node. And we finished off by printing the last value and also an end line. Now we'll look at the find function. So here we set this temp value to the first node, and this int ID is going to be the thing that we hopefully return. So we basically loop through all of the nodes until we hit a null pointer, and we see if the node's value is equal to what we're looking for, we'll just return the index. Otherwise, we'll increment ID, and we'll also advance the pointer. Alternatively, you can do this with a for loop and just loop through from 0 to length of the linked list. And it could be simpler in some ways, but this also works. If we don't find the index, we return -1 to show that it's not in the linked list. All right, so that basically covers all of the linked list functionality that we have here. Let me know if you want to see this class, this set class, and a few other things here like a stack, a queue, etc. But it's basically, to sum it up, mostly the same functionality as our linked list. I can just go over this in a few minutes, but basically our stack, it just uses the same push, pop, etc. Some of the things are just renamed, so if you type stack.top, it'll just look at the back of the stack. And then in the class, it's again almost the same stuff. The priority queue is a little bit more advanced because everything else is the same except the push method. Because when you push in a priority queue, you want to make sure that you push it to this in a sorted position. So you need to like loop through and check exactly which position you should insert your new element into. You can do this with a binary search, or you can do this with a linear search. Since this is a linked list, we can't easily use binary search since we don't have pointers to every single node, so we use a linear search here. We also have this map which inherits from linked list, so you can insert with a key and a value, and then also get with a key, and remove. I won't go into this in a lot of depth, but it basically uses the same functionality as the linked list. So here, if we don't find anything with this key, then it adds it to the map. Yeah, so there's basically that functionality. The unordered map is pretty different from the linked list. It doesn't inherit from the linked list, and it uses this key value pair instead of the nodes. And that's basically it. That sums up this file. There is this in the description, as I said, if you want to take a look at this big document. It's a bit more advanced with templates and stuff, but I recommend if you're learning like slightly more advanced C++. I know this isn't super advanced using templates, but if you're interested in learning how these work, then I recommend just going to the GitHub, downloading this. And I have in the main method down here a bunch of tests so you can see how it works and mess around with these. And yeah, this is like 1,300 lines of code, so I don't recommend you read all of it, but just kind of skip to what you want to see and whatever seems interesting to you. Like here I have this matrix, which is just a 2D array basically with some functionality. Up here is the linked list that we just talked about, and you should recognize like a lot of the code here that we just discussed, so that should be quite interesting. Additionally, in this GitHub, I have this advanced data structures.cpp. So in here there's like trees and sets and stuff like that, slightly more advanced stuff. So if you want to look at this as well, feel free. It's a bit shorter, but still about 600 lines of code. I recommend you play around with these and maybe watch some YouTube videos. It's really interesting stuff about data structures and algorithms. So yeah, that's basically it. Thank you for watching. Make sure to like and subscribe, and have a great day.